That's right. Thank you for the introduction. So yeah, I'm Ignacio. I'm going to talk about calibration of a unified parameterization of turbulence and convection for climate models. So first, why do we care about turbulence and convection? Well, these are processes that strongly affect the vertical transport of heat and moisture from the surface to higher levels of the atmosphere. And so they're intimately related to the occurrence of clouds in the atmosphere. And as we've seen in earlier talks today, clouds are a very important part of the climate system. Now, the problem is that if we wanted to actually resolve these clouds, or at least the dynamics of clouds, not the microphysics, in climate models, we would need resolutions of the order of tens of meters in each direction. And if we consider the resolution that we have now in current climate models, which are typically tens of kilometers in the horizontal and tens to hundreds of meters in the vertical, then we would need a 7 order of magnitude increase just in spatial resolution to resolve this. So this is not going to happen now or in the near future. So there's still going to be that need to model subgrid scale processes in climate models. Now, of course, parameterizations of turbulence and convection already exist in climate models, but the main problem is that there are still large biases associated with low cloud cover in climate simulations, and part of those biases can be tracked back to these parameterizations. So some of the causes of the error in these parameterizations may be due to the fact that there's no interaction typically between processes in these parameterizations. So we might have parameterizations of turbulence and convection, which are different and do not interact at the subgrid scale level. And there might also be unphysical switches in the model. And here I'm showing that on the figure, where we might have parameterization for boundary layer turbulence in the bottom levels of a GCM column. And then we might have a switch that activates a convective parameterization above that. So what we'd like, our desired solution would be to have a unified parameterization that allows a consistent process interaction at the subgrid scale from an interaction between the turbulent and convective processes. And we would also like a parameterization or a model that is sufficiently flexible and general to actually be able to learn from data and reduce the biases that we encounter today. So a candidate for this unified model is the eddy diffusivity mass flux scheme, in which we subdivide every GCM grid box, as I'm showing here in this schematic. And we subdivide it into different subdomains. One of them in red represents the convective structures in the atmosphere, or updrafts, downdrafts, or plumes. And the other subdomain, which is characterized by more isotropic eddying motion, we'll call the environment. Now, if we take this picture into the statistical moments of any variable phi in the grid box, we can see that we can subdivide this grid mean into subdomain means of each of the same variable. But what's interesting is that now if we consider the higher order moments, in particular here I'm considering a covariance or vertical flux of phi, we not only obtain a weighted mean between the covariances in each of the subdomains, but we also obtain a term that depends on the difference between the subdomain mean terms in each of the subdomains. So if we look at this decomposition physically, we can see that the two first terms are representative of turbulence that is occurring within each of the subdomains, and the latter is representative of convective, more large-scale processes. So the Admx scheme provides a framework in which these turbulent and convective processes can interact.
Ignacio, do you want to go to presentation mode? You want to switch?
Oh, okay. Yeah, I can do that. Yeah.
Okay.
Okay. That's better. And so, as any other turbulence and convection model, the Admx scheme has closures. So in particular, we need closures for the mass exchange between the subdomains, which are entrainment and detrainment. We also need closure for the momentum exchange between the different subdomains, which is typically done through the pressure gradients. And also we need closure for the turbulent mixing within each of the subdomains, which is done through an eddy diffusivity. I will not go into much detail about the closures that we use, but what's important here is that these closures, as in any other model, have free parameters, and those free parameters can be learned from data. Now, learning these parameters, which I call theta here, from data can be formulated as an inverse problem, in which we know we have the output y, which in our case are going to be observations from LES data, so synthetic observations. And in particular, we can use, for example, vertical profiles of state and subgrid scale fluxes after some time from initialization for different initializations and forcing. And having that y, we want to learn the inputs of some forward map, which I call here G, that allows us to reduce the error between that map and y. And so in this case, our forward map is the Admx Scheme in a single column model, which allows us to compare results with LES in a single GCM column. And theta here are the parameters that we want to learn. In particular, I'm going to be considering a 9-dimensional space for the results that I'll be showing next, where 3 of those parameters control turbulence, 3 control the mass exchange, and 3 control the momentum exchange in the Admx Scheme. And our objective here in this problem is to find the maximum a posteriori of theta and a measure of uncertainty also around that point estimate. So this problem can be framed in the sense of a Bayesian inference problem, where we could just sample from the posterior using Markov chain Monte Carlo and obtain both the map and uncertainty around it. The problem with this approach is that MCMC, as we've seen in earlier talks, typically requires hundreds of thousands, if not millions, of model evaluations. And this can become a problem if the forward model is expensive, because then this becomes prohibitively expensive. And generally, this is not going to be a feasible technique for online learning. So if we want to do this once, it's okay. But if we want to do it as we simulate climate, for example, it's not going to be feasible. So an alternative to this approach would be to use the calibrate, emulate, sample approach, which has been recently proposed, in which at first we treat this as a sort of optimization problem, where we just want to obtain a point estimate of the map. And we can do this with inexpensive ensemble methods, such as ensemble common inversion. After this, we use the data that we've generated in the ensemble process to train a cheaper emulator than the forward model. So we can, for example, think about a Gaussian process or a neural net here. And then finally, we use that cheaper emulator to sample from the posterior. And this is going to be much faster than sampling for the forward model. And this, in this later stage, is where we obtain a measure of uncertainty for our model. Now, here I'm just showing results for what a calibration stage would look like using ensemble common inversion, where we have to minimize some loss function that depends on the likelihood of the data given our model, and some regularization term that depends on our prior. And I'm showing here that with an ensemble method, we can start with different numbers of particles in our ensemble, and typically we'll reach convergence to an estimate of the map in about 5 to 10 iterations of this process, which multiplied by the number of particles gives us around 100 to 1,000 evaluations, which is much cheaper than millions of evaluations for MCMC. And then here on the right-hand side, I'm also showing that in ensemble methods, we not only converge to the map, but we also, all the particles in our ensemble are converging towards the map. And so here what I'm showing is the radius of a minimum volume sphere that contains all of our ensemble points in parameter space. And so we can also see that those particles are reaching a consensus. So once we have the parameters that we've learned at that point estimate, we can use that in our model and comparing the physical space to the results from LES. So here I'm just showing examples of vertical profiles of potential temperature and total water specific humidity with LES, and we can see that the Admx Scheme performs really well when after it's been trained with this technique. But at this point, we only have a point estimate of the parameters, and we do not have any information about uncertainty from the calibration stage. So this is where we have to turn to the next stage, which is the training the emulator, where we will use the data that we generated in the calibration stage. Here, we're not performing any additional forward model evaluations. But what's important to note here is that we typically don't want to use the information that we generated in the later stages of the ensemble common inversion, because it's too converged, so it doesn't give us any information about the posterior landscape. So we'll want to use the earlier stages of the ensemble common process to learn. And this number of stages that we'll need, of course, depends on the number of particles that we have in the ensemble. If we have more particles, we'll need less stages to train, and on the number of parameters that we are trying to learn. And of course, this number of stages that is needed to train an emulator can be obtained through cross-validation of the candidate emulators. The final stage in this framework is sampling. So here I show the results from Markov chain Monte Carlo view for 3 different parameters from Gaussian processes using a Gaussian process. And here what's important is that now we can actually perform millions of evaluations in a matter of minutes, because Gaussian processes are very, very cheap to evaluate. And another interesting property here is that in general, we can design the kernel function of a Gaussian process so that the posterior is somewhat smoother than the original posterior from the forward model, so that we can actually sample from this posterior even more efficiently. And just to emphasize again, no model evaluations are needed in this stage, nor in the emulate stage, only in the calibration. But through these later stages, we can actually recover the information about correlations and uncertainty that was lost in the ensemble common inversion, which is only an optimization method. So finally, to sum up, I've shown here that we can learn the free parameters in an ADMF model from, in this case, sorry, from time averaged vertical profiles of state variables. I've shown that the calibrate emulate sample strategy provides a map, estimate, and uncertainty quantifications of parameters at a very low cost, so thousands of evaluations instead of millions of the forward model. And the next steps that we'd like to take are to use a more comprehensive set of large AD simulations around the globe to actually train our model and test our model, because here we've only used 5 to 10 cases to actually train our model, which are available to us right now. And in the farther future, we'd also like to demonstrate this framework in an online learning setting, which I'm showing here on the picture on the right, where we will have a GCM that is running climate simulations, and we would embed LES in some of the columns of that GCM, which are forced by the GCM. And while we run those LES simulations, we can at the same time learn uncertainty and about the parameters for our ADMF model from those LES simulations. And with that, I'll take any questions.
All right, great. Thank you, Ignacio. Any questions? Marcus had a question.
Yeah, really nice talking, Ignacio. Do you have a sense for how you'll integrate satellite observations? Like, I understand that these parts can be tuned with something like LES, but do you plan on then retuning once you have, say, satellite observations and a full atmospheric model or a full Earth system model?
Right. So that's a very good question. So right now, as you said, we have LES simulations, so we have a lot of output that we can use for learning. So one of the things that we want to do is to try to see what of those outputs are more important for learning and can actually make our model learn. And once we have that, we'll consider, can we actually observe those outputs? And once we have that answer, that's when we would go to satellites and use the information from there. Yeah.
All right. Any other questions? Okay, so there's a question by you. Structural uncertainty was a theme of some of the other talks. Any comment on this for your problem? Like uncertainty in the closure assumptions themselves, not necessarily the closure parameters.
That's a good question. So for now, we are encoding all the uncertainty in this term. So we're just saying that uncertainty is additive and is proportional to some kind of noise. So of course that might be too strong of a simplifying assumption, and that is something that we'll be studying next. But for now, we are assuming in this learning process that we have a perfect model. It doesn't have structural uncertainty, but of course that is not what happens in reality.